Hello friends, welcome to CEC Gurukul live lectures. Dear friends, today in this session we are going to talk on classical mechanics in detail. In the previous session we had a vivacious session where we discussed about what classical mechanics is, taking the series, that is the topic forward. Today also we are going to have in-depth knowledge on the following topic. Friends, for the discussion we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is Assistant Professor and she is teaching in J.C. Bose University of Science and Technology. If you wish to ask questions from Dr. Sonia Bansal on classical mechanics, feel free to talk to us through our toll-free number. Our number is 1800110430. I repeat, our number is 1800110430. Now, I would like to welcome our guest, Dr. Sonia Bansal, once again. Hello, ma'am. Welcome to the lecture.
Dear student, we are discussing about the classical mechanics. In the part 1, we discuss about the elementary idea, in which the formulas which are used in the classical mechanics, where we discuss about the single particle system, multiple particle systems and its constraint, where we discuss about the basic principle and basic phenomena behind the classical mechanics, in which, as I recall the previous lecture, where we discuss about the total angular momentum here for the multiple particle system, where we have the law of action and reaction. On the basis of that, we can define the that what type of forces are acted upon this action and reaction, laws of action and reactions. And we know that if we have a weak law of action and reaction, then the momentum will be conserved. P is a momentum and will be conserved. If we talk about the strong law of action and reaction, then there is a conservation of the L, angular momentum. Then always see in the previous lecture that there is no special origin and no special orientation, and we accepted that the symmetries and the fundamental principles, all forces must satisfy the action and reaction. That is the third law of Newton's. After that, we define for the total angular momentum for the i's particles or the number of particles, and then we discuss about the energies, kinetic energy and the potential energy. In the kinetic energy, we will find the kinetic energy for the two system, where T2 minus T1, position of the particle at one position and the second position, and then we calculate the total kinetic energy. After that, we calculate the potential energy. Then we find out energy conservation, where we having that the second terms in the internal potential energy, which depends upon the distance between the two pair of particles, and the constant of the particles relative configuration is the fixed, that is define the rigid bodies. Now, today's lecture we define the classical mechanics part 2, where we discuss about the Lagrangian equations, D'Alembert's principle, and how they are dependent and independent. That all will define in this lecture. First, we start with the constraint. What are the constraints and how they are helpful in the further equations. What is a constraint? Here we know that the equation of motion, where we assume that all the particles can move in a space anywhere, but this is not true generally. We can constrain the particle also, so not generally true. And here we have the equation of motion, MIRI double dot is equal to Fi, that is a force applied to the particle and its work on the motion, and we are having Fi E plus summation J F J I. J is another particle which is exerting force on the ith particle. But here we are saying that the particle motion is anywhere in this space, but it is not generally true. In fact, we can say that the free spaces is an idealization. And if we take some two examples, if we take the amusement park ride constraint, hopefully on a trail, and billiard ball on a pool table, then we can constrain is motion here. Then how can they constrain the equation? It depends upon the type of constraints which are using to constrain the motion, that we will define. We also defined in the previous lecture, that is a holonomic constraint and non-holonomic constraints. Here we define in that constraint may be expressed by, this is a force R1, R2, R3 and up to t which is equal to 0, which is defined the holonomic constraint, means where we just put it constraint here, we put it is equal to 0. Now particle on the xy plane, particle is moving only in the xy plane, so z is equal to 0. For the rigid body, we have Ri minus Rj whole square minus Cij square is equal to 0, that we already defined. All other cases are called the non-holonomic. Apart from this, if z is not equal to 0, then it will becomes under the non-holonomic. It means we do not really want to mess it by just taking the another parameters. Maybe inequalities such as z is equal to or greater than equal to 0, and may depend on derivatives such as Ri dot, means non-holonomic constraint depend upon the derivative of position vector. Here we are having the position vectors, not derivative of that. Now we will deal only with the holonomic constraints. Now, what are the independent variable? In the non-holonomic constraint, when we reduce the number of independent variable by 1, then we can have can have the particle in x and y, because we are having z is equal to 0. Now we may able to solve the constraint for only the one variable. Here we see that f Ri, R1, R2, R3, T is equal to 0, which is equal to x1. Here we see that in the holonomic constraint we are using one independent variable, that is x. Here x1 we can write it as g, y1, z1, r2, r3 and t. It means here R1 will be replaced by the Y1, Z1, and it will explain the X. They can also drop this variable. You may have to switch the different set of the variables, like for a particle in the sphere, we have x square plus y square z square is c square, and this is a good choice for theta and phi, that will define the angular in the angular terms. Now, new set of variables which we use are the generalized coordinate. Generalized coordinate basically defined by the degree of freedom. Here, if we are having the n particles and they are having the 3n degree of freedom, now we are having the holonomic constraint, that is k. This constraint reduces this equation into 3n minus k. It means 3n is the degree of freedom and k is the constraint. It means in any particles it is moving in 3n directions, but it's having a constraint in k dimensions. Now using generalized coordinate we can write it again, q1, q2, q3n minus k. Now Ri we can write it as Ri, q1, q2, q3, q1, q2, q3 and t. Transformation equation from RL to the QL. It means these are the generalized coordinate. Here we are having that this R coordinate will be replaced by the generalized coordinate, which is represented by the q1, q2, q3 and time period we are having. Example, we are having transformation from x, y, z coordinate to the Cartesian coordinate to the angular coordinate. We have x is equal to c sin theta cos phi, y is equal to c sin theta sin phi, and z is equal to c cos theta. Now from the previous equation we have Ri, Mi, Ri. This is a very common equation in the classical mechanics. We define the force exerted on a ith particle, which is Mi Ri double dot is equal to Fi E plus, this is the external force exerted on the I particles, and this is the Fji, jth particle exerted the force on the ith particle. And now we can include constraint in the previous equation by switching to the generalized coordinate, where we replace Ri with the Ri, Qy, Q2, Q3 and the T. Here we see that this Ri, this coordinate, this these coordinate will be converted into the generalized coordinate, and where we are having the constraint. Holonomic constraints is introduced in any system, then the coordinate will switches to the generalized coordinates. That's why Ri is equal to Ri Q1, Q2, Q3 and T. We are introducing the constraints also. How can we transform the equation to the generalized coordinates? That equation is known as the Lagrange's equation. What are the Lagrange equation? Means why constraints are introduced in the position of the movement of the particles. The constraint is an idealized classical concept. It is not as uncertainty principle in quantum mechanics. It is useful to switch between the coordinates, where we see that R is replaced by the R, Q1, Q2, Q3 and T, and where Q1, Q2, Q3 are the constraint. Define the constraint. Constraint and the forces. What effect on the forces when the constraints are introduced? A holonomic constraint is an infinitely strong forces or an infinitely high potential well. That's why it produces a constraint. To produce a constraint in holonomic, we consider the high potential well, infinite high potential well. And it is a smooth where electron of example are the electron of a hydrogen atom. Here we see that this constraint where VR is the potential, and this side we are considering the moment of the particle, but here this side it is free, particle is free to move, but here we are having the constraint in the x-axis. Constraint is defined and it is moving free in the y-axis. It's still true that the electron feels strong radial binding forces while it can move freely around the nucleus, and binding forces make the r direction spatial. Movement of the particle will be the spatial. Here we see that this is the VR potential versus distance curve which define the movement of the particle. The force and the symmetry. Without the forces, all the coordinates are equal. Means we are introduce the constraint in x direction. If we are not taking the force, then x, y, z is moving simply in all the direction. Forces break the symmetry, means some coordinate system works better than the other. Generalized coordinate offer the natural way of handling the system with such forces. Then constraints are extreme cases when we develop the techniques for the movement of the particle. For this, we define the Lagrangian equation, where we define the generalized coordinate, which is sandwiched in between the normal equation of the classical mechanics. Here we see that d by dt del L by del Qj dot minus del L by del Qj is equal to 0, where L define the Lagrangian, and this equation is known as the Lagrange equation, which is equal to L Lagrangian. Here we are defining the Q, which is a generalized equation, generalized coordinate Q, Q dot and T with respect to time. This is Q and derivative of Q, and T which is equal to T minus V, means kinetic energy and the potential energy. We define the Lagrangian L is equal to T minus V in terms of generalized coordinate Qj, and there are time derivatives Qj dot and the time. This Lagrangian equation defined the generalized coordinate Q, the time derivative of Qj dot and the time period, which is equal to the kinetic energy minus the potential energy. The potential energy V is defined by the VQT. Here why we are defining the VQT generalized coordinate in the potential, because here we see that here we are having the constraint in the motion of the particles in terms of the potential. That's why here we define VQT. Q is generalized coordinate, and then we can write it as all forces must be conservative, as we already discussed. Let us example how it works. Now consider a particle on a line, which is moving on a line, particle moving on a x direction, moving in the one line. We know that d by dt, this is the Lagrangian equation, del L by del Qj dot minus del L by del Qj is equal to 0. Now a particle moving along the x-axis. Now x will be xt, dependent upon the time. Y is equal to 0 and then z is equal to 0. It means the particles are moving only in the x direction, but it is not free to move in the other directions. Now potential. Now we will calculate the potential energy, the kinetic energy in the x direction. So simply we are having the kinetic and potential energy T is equal to m by 2 1 by 2 mv square. We know that kinetic energy is 1 by 2 mv square. That's why we are adding m by 2 x. It is moving in the x direction, distance, and we take the square of that. We will have the velocity x dot square v is equal to vx. The potential will be in the terms of the x-axis. Now we can write L is equal to T minus v. We put the value of T here, m by 2 x dot square minus vx. This explains the particle is moving in the x direction or moving in a line. Now Lagrangian equation now become mx double dot means mx ma square plus del v by del x is equal to 0. After solving this, we are having this. Lagrangian equation will become this. Here we put all the values and then we will find out that mx dot plus del v by del x is equal to 0. Equation equivalent to the Newton's equation given by fx is equal to minus del v by del x. What is explaining that the Newton's equation will now become fx is equal to minus del v. In terms of the potential, we will define the Newton's equation. Lagrangian equation, which derive the Lagrangian equation from the Newton's equation, and then we discuss about the new introduction of the Hamiltonian principle. For that we will discuss about the D'Alembert law. Lagrangian equation, we know that this we already defined that L q dot t is equal to t minus v. Lagrangian will be difference between the kinetic energy, the potential energy, and here we are having the constraint which is in the form of the q, time derivatives of q and the time. Now we have the virtual displacement in terms of the constraints. Let us consider a system with the constraints: ordinary coordinates defined by the Ri, generalized coordinates defined by the Qj. The ordinary coordinates Ri is I is equal to 1 to n. We are having the n coordinates in the ordinary coordinates. We are having 1 to n coordinates and were defined by Ri is the position coordinate. I is equal to 1 to n. But here in the generalized coordinate we have Qj, j, the value of j is equal to 1 to n. This is without the constraint. Here we are having the constraint. Then we are having from 1 to n, we are generalized coordinate is 1 to small n. Imagine moving all the particles. We are having Ri, that will be the Ri plus del I. That del Ri define the virtual displacement of the particle. Similarly here for the generalized coordinate we can write it as Qj is equal to Qj plus del Qj. It means we define for the virtual displacement with the ordinary constraint. That virtual displacement is introduced with the ordinary and the generalized coordinate. Here we see we define R1 is equal to R1 with the generalized coordinate. This is R2, R2, Q1, Q2, Qt, and Rn is equal to Rn, Q1, Q2, Qn. This define the ordinary coordinates which converted into the generalized coordinate by introducing the constraints. This is the virtual displacement. We imaging the moving all the particles slightly with the virtual displacement, and we introduce virtual displacement in the ordinary coordinates and in the generalized coordinate. We know that this virtual displacement must satisfy the constraints also. Means here we are having del Ri, then this must constrain the n coordinates which are independent. This is 3n coordinate not dependent, but here summation I del Ri del Qj and del Q curl Qj and del Qj, that will be the n coordinate independent. Now this term, which is the virtual displacement for the ordinary coordinates, converted into virtual displacement of generalized coordinate. Now what is D'Alembert's principle? D'Alembert's principle is defined from the Newton's equation. We know that the Newton's equation of motion Fi is equal to Pi dot is dp by dt, that we will define Fi minus Pi dot, we can write it as a, we take the P this side, which is equal to 0. This is the Newton equation. Now part of the Fi must be due to the constraint, which defined by the Fi is equal to Fi is the applied force on the I, and Fi, this small Fi define the constraint force on the Fi, which is the force on the particle I particles. This is the applied force and this is the constraint force. Applied force we can define Fia is equal to Fia Ri R2 Ri Rn T. This is the ordinary coordinates that define the applied forces, but constraint forces Fi usually does not work. Its movement is perpendicular to the force. That's why Fi del Fi virtual displacement is equal to 0. Exception is the friction that produces a constraint in the movement of the particle. Now multiplying Fia is Fia plus Fi minus Pi is equal to 0. Here what we do, this is the force equation. This is the Fi is equal to Fia plus Fi. Now Fia plus Fi minus Pi, because here we put the value of Fi from the previous equation Pi for the define the force equation of the motion. Now we multiply this by dRi, because we are finding the sum of all over I. Here we are having Fia plus Fi. If it is equal to 0, then movement is perpendicular to the force. This will be multiplied by the del Ri. Hence we have summation I Fia minus Pi dot into del Ri is equal to 0. That define the constraint force is out. Here we just not including the constraint force, that is the Fi del I is equal to 0. Force of constraints dropped out because Fi del Ri is equal to 0. From the previous equation, moment is perpendicular to the force, this constraint force is equal to 0, and from this equation we drop this. As we multiply this equation by del Ri, this will be Fia del Ri, Fi del Ri and minus Pi del Ri. This Fi del Ri will be 0. The similar equation we are defining here. Then Fia minus Pi dot del Ri is equal to 0, and which define that the constraint force is dropped out. This is known as the D'Alembert's principle. We are not having the constraint in this movement of the particle, which is Fa, which will be the summation of I Fia plus Pi del Ri is equal to 0. Now we switch from the Ri to Qj. First term we have summation Fi, second term we have summation del Ri del Qj, and del Qj which is equal to summation of j Qj del Qj. That we will replace with this term del Qr del Qj and Fi, that will define by the Qj. This is a capital Qj. We define the generalized force on the particle. Unit of Qj is not always a force, it can be work, always work. Qj is define the generalized force and Qj is the constraint. In the second term, this is the first term where put the value of Fi. This term will be del Ri Qj and del Qj. Now we take the momentum term from the equation. The second term will be summation I Pi dot del Ri is equal to summation I Pi dot summation j del Ri del Qj. Here again we are putting this value del Ri here, which will be summation j Q Ri Qj, that j define the constraint del Qj, j are the constraint terms, is equal to summation. Now this can be written as summation ij mi ri double dot del Ri del Qj, and this will be the del Qj. Here we put Pi is equal to mi ri. Now we can adjust it, and we know that Ri del Ri del Qj minus d by dt, this we will open this equation in terms of velocity. Here we have d by dt del Qj vi square by 2 minus del Qj vi square by 2. If we see that we can cancel it, then we can have this value. We replace this Ri del Ri by Qj. Now solving this, we have this second term will become, by putting this value in the above equation, this value will be replaced by this value. The final equation for the second term, we have summation j d by dt del t by del Qj dot minus del t by del Qj, and it is the del Qj. We know that t is equal to mv square by 2 and I for the ith particles. Finally, the D'Alembert principle will become, in terms of the kinetic energy, it will be summation j d by dt del t by del Qj dot minus del t by del Qj minus Qj del Q. This we can put from the previous equation. This we can put the Qj, and del Qj is equal to 0. That define the D'Alembert's principle of the multiple particles. This summation I d by dt del t del Qj dot minus del t by del Qj minus Qj del Qj is equal to 0. It means the particle motion depend upon the kinetic energy and the constraints also. Lagrangian equation, these are free, so we can from the D'Alembert's principle we can see that these are free. It means generalized coordinate Qj are independent, and this d by dt del t by del q dot minus del t by del q is equal to, we can write it as Qj. This is this will be Qj is the force due to this Qj. Here we know that the generalized force, and this equation, this kinetic energy is equal to generalized force. Assume force are conservative, we know that Fi is equal to minus del I V. So we have Qj is equal to summation I Fi del phi Ri del Qj. So this will become minus, we replace this Fi with minus del IV, that is the potential energy, del IV curl Ri curl Qj, which is equal to minus curl V by curl Qj, and again this will be equal to this value, that will be the Qj. It means d by dt del t del Qj is minus del t Qj is equal to Qi, that is a force. Here we also define Qj in terms of the potential, in terms of the kinetic energy. So Qj can be replaced by minus del V by del Qj. So Lagrangian equation now will become, we put this Qj value here, minus del V Qj. So we can write it as d by dt del t by del Qj dot minus del t minus V Qj, del Qj is equal to 0. We assume that V does not depend upon the derivative of Qj. What is Qj? Qj is a derivative of generalized coordinate. Here not we don't have any Q dot, so the potential of particles do not depend upon the generalized coordinate. So we can write it del V by del dot J is equal to 0. The final equation from the above, we can write d by dt del L by del Qj dot minus del L by del Qj dot, that will be L is equal to T Qj minus Qj dot Qt and V Qj T, that is the Lagrangian equation. This is Lagrangian equation in terms of the potential energy and the kinetic energy. Here we see that this Lagrangian equation on the angular momentum, which is equal to the difference of the kinetic energy and the potential energy. From this equation we can say that this kinetic energy, these constraints depend upon the this constraint can explain in the kinetic energy. Here we see Qjt, where we don't have a time coordinate. Qj is the generalized coordinate. Similarly here we have the kinetic energy dependent upon the generalized coordinate. Kinetic energy depends upon the derivative of the generalized coordinate and the time period. But here the potential energy dependent upon the generalized coordinate, not on the, here we are not having the term of Qj dot, not on the time dependent generalized coordinate, depend upon the time also. That's why we can write it as L is equal to T Qj dot T minus V Qj in and T. This is the Lagrangian equation. What are the assumption behind that? The constraints are holonomic. So we write it as Ri is equal to Ri, Q1, Q2, Q and T. Constraint forces do not work. That's why Fi del Ri is equal to 0. Means forget the frictions also. Constraints not always work, that we define in the D'Alembert's principle. Applied forces are conservative. That's why Fi is equal to minus del I V. V is the potential. Lagrangian equation itself is okay if the V depend explicitly on the T. It means V depend upon the T. Potential V does not depend upon the time derivative of the generalized coordinate. That's why del V divided by del Qj dot is equal to 0. These are the assumptions for the D-element principle by using the D-element principle and the Lagrangian equation. Constraints are holonomic. Constraint forces do not work. applied forces are conservative, potential V does not depend upon the derivative of the generalized coordinate. Now we take the example. Here we take the time dependent example. The transformation function may be depend upon the time t. Generalized coordinate system may move where we define Ri is equal to Ri Qj t. For example, coordinate system fixed on the earth, that is example all the system x, y, z are fixed on the earth. Now we are having a spring which is having the constant k and having the length L, and the mass of this rail or this object is m. So here if we stretch it and this is the angular velocity, then it will be the L plus r. L is the natural length and r is the coordinate. How stretch is with the coordinate, generalized coordinate, and the length. Now time dependent example again. The transformation function will become x is equal to L plus r cos alpha t and y is equal to L plus r sin alpha t. Transformation function means we are having the x coordinate and y coordinates, and we are talking that this is a time independent. Then transformation function will become x is equal to L plus r cos alpha t, y is equal to L plus r sin alpha t. The kinetic energy will become T is equal to m by 2, because we are taking the constraint in x and y direction, that we are taking the movement of the particle in x and y direction. So we take m by 2. Kinetic energy is 1 by 2 mv square, v square for the two coordinates x square and y dot square is equal to m by 2. We can write it as r dot square plus L plus r square alpha square, means we are putting the value of x and y in this equation, derivative of x and derivative of y in this equation, and we will find r dot square plus L plus r square alpha square. Now potential energy will become V is equal to k r square. What is k? K, here we define the spring constant, and it will be k by 2r square. Now D'Alembert's principle. Now we have the L is the Lagrangian equation, will become m by 2, means t minus v. So we put the value of t from here to this equation, put the value of v from this equation to this equation. It will become L is equal to m by 2 r dot square plus L plus r square alpha square minus k by 2 r square. The finally Lagrangian equation will become d by dt del L by del r dot minus del v by del r is equal to m r double dot minus m alpha square L minus L plus r plus kr is equal to 0. This will be solved. Then angular momentum will be solved in the Lagrangian equation for the time dependent particle. It will be mr dot double dot minus m alpha square L plus r plus kr is equal to 0, where the system is time dependent. Now we can adjust it as this will be the mr double dot minus m alpha square 1 plus r plus kr is equal to 0. So we take this term common as a k plus m alpha square. We multiply with this equation by the k minus m alpha square and divided by k minus m alpha square. Then we have this equation. Now we spring constant, if k is greater than m alpha square, then a harmonic oscillator with frequency omega is equal to, angular frequency omega is equal to k minus m alpha square by m. And if k less than m alpha squares, it will move exponentially always. These are the conditions on the basis of we can define the oscillation of the particle. If k greater than alpha square, then we are having the harmonic oscillators, and if k less than m alpha square, it moves exponentially. If k is equal to m alpha square, then velocity will be constant, this term, that is the centrifugal forces balances with the spring forces. Now we have some Lagrangian we have some arbitrary conditions for the Lagrangian, where we define Lagrangian is not unique for a given system. It means if the Lagrangian L describes a system, particular system, then L dash is equal to L plus dfqt divided by t. It's work well for any function f. So it is not unique that Lagrangian is applied for a particular systems, but it can be used for all the systems also. Now, or one can prove this by using the del by d by dt del dq dot df by dt del by del q df by dt is equal to 0. Now this equation will be df by dt. We can write it as del f by del q dot plus del f by del t. Means we are introducing the constraint in this force which is acting upon the system. On the basis of that, we can have some assumptions like constraints are holonomic, constraints forces do not work, applied forces are conservative, potential V does not depend upon the Q. Then we have velocity dependent potential. Potential does not depend upon the derivative of generalized coordinates. Then we have velocity dependent potential. We know that Qj is equal to minus del V by del Qj, potential with the constraint coordinate. And we can write it as del V by del J is equal to 0, so that we can write it as d by dt del t by del q dot minus del t by del qj is equal to qj. Lagrangian will become this part, d by dt del t minus v del qj dot minus del t minus v del qj is equal to 0. It means this part, this v, here we know that del v by del qj is equal to 0, so this will be the 0 value. Then qj can be written as minus del u by del qj plus d by dt del u by del qj dot. Now what is this u here? U define the generalized or the velocity dependent potential. It means this potential now dependent upon the velocity of the particle in a system. So if we talk about the dependence of the velocity, then this potential will be 0, and then this will be replaced by t minus v replaced by the u, and u define the generalized or the velocity dependent potential, which also depend upon the generalized coordinate, time dependent generalized coordinate, and the time period. Now the Lagrangian equation will become L is equal to T qj dot T minus u. U is the velocity, generalized velocity, which depend upon the potential, and now this velocity will also depend upon the derivative of the generalized coordinate, that is qjt. If we have the question to write in generalized velocity dependent potential, where we can define the dependence of the derivative, time derivative, then we have L is equal to T qjt minus u qj dot and t. Previously we have defined L is equal to T qj dot t minus v. This v replaced by this velocity dependent potential, which is u qj dot and t, which is dependent upon the time derivative. Fm force, electromagnetic force on the particle, where we are having the Lorentz forces on the charged particle, which can be defined by F is equal to Q. This is the Maxwell equation. We know that F is equal to Q E plus V cross B. Velocity dependent, this is velocity dependent, cannot find a usual potential equation. We are talking that this Lagrangian equation dependent on the velocity, so we take this Lorentz force on a charged particle, which defined by F is equal to Q E plus V into B. E and B fields are given by, means electric field and the magnetic field, while defined by E is equal to minus del phi minus del A by del T, and the B is equal to del cross A. Force V dependent, velocity dependent, need a velocity dependent potential. So we can write it as U is equal to Q phi minus Q A into V. That is the force dependent value. So now we can write the Lagrangian in terms of electromagnetic force on a particle. It will become L is equal to 1 by 2 mv square minus Q phi plus Q A into V. That will depend upon the electric and magnetic field also. So we replace this potential with the Q phi, this potential which is the velocity dependent, will by the Q phi plus Q A into V. This is the forced part. This is the electromagnetic force particles movement, and the Lagrangian terms will define by the electromagnetic force which is acting on a particle. Monogenic system, where all forces in the system are derived from the generalized potential. That generalized potential which depend upon the velocity, and then it is called the monogenic system. If the all forces in a system are derived from the generalized potential, that is U, then this system is the monogenic system. This is the monogenic system. U is a function of Q, derivative of Q, generalized coordinate, derivative of generalized coordinate and time. Then Lorentz force is the monogenic. So Qj is equal to minus curl U curl Qj plus d by dt curl U by curl Qj dot. A monogenic system is conservative only when this potential dependent generalized potential energy is equal to UQ. It means this potential velocity dependent potential energy dependent upon the generalized coordinate. This generalized velocity depend upon the generalized coordinate. So we can write it as del U by del Q dot is equal to del U by del T, which is equal to 0. Lagrangian equation now works on the monogenic system. That will define for the monogenic system where we are having the potential energy which is dependent upon the velocity. Now Hamiltonian principle. We derive the Lagrangian equation from the Newton's equation using the differential principle. D'Alembert's principle uses the infinitesimal displacement. It is possible to do it with the integral principle. Here we have the differential principle. Now in the Hamiltonian principle we use the integral principle. It means the Newton equation we use integral principle, and then we can solve the Hamiltonian principle. For this we have the configuration space, generalized coordinate. We know that Q2, Qn fully described the system's configuration at any moment. A generalized coordinate in any system will define the configuration of any moment. And if we imagine the n-dimensional space, means we are imagining the configurational space where we will define the generalized coordinate, then each point in this space defined by Q1 to Qn, corresponding to one configuration of the system. The time evolution of the system from a curve is configuration space will be defined here. This is the real space where all the particles are moving, but here the configuration space, the particular coordinates will be defined, or the constraint coordinates defined for the system. That is the fully describe the system. Here we are saying that if the system fully dependent on the generalized coordinate, then system is in the configuration space. We are having the n-dimensional space, so it can be possible in the n-dimensional space also. So this is the configurational space where the movement of particle takes place. Now we are taking the integral. In the previous where we defined the Lagrangian, we consider the differentiation. Now for this Hamiltonian we define the integral part. Again we are having a system which is in motion, then the system is moving with the coordinates qj is equal to qjt, where j can be 1 to n and t is the time period. Lagrangian can be defined as L q dot t, all are the time dependent, that's why you can write it as qt q dot t and t. We take the integral part, that will be the I action or the action integral for this defined by time constraint t1 to t2, that will be the LT, t1 for initial and t2 at the final. So t1 to t2 will become LT. Action I depends on the entire path from initial to final. So we have t1 to t2 L dt. Now choose a coordinate is not we can choose any coordinate from qj. Action is invariant under the coordinate transformation. What is a Hamiltonian principle? The action integral of a physical system is stationary for the actual path. Then this is equivalent to the Lagrangian equation, for we can prove it for the stationary path. Integral, the action integral of physical system, is stationary for the actual path. Here we see in this equation that this is the constraint, this is the actual path which is followed by the particles to move from 1 to 1. This is equivalent to Lagrangian equation that we will prove. The three equivalent formulas we use here. First is the Newton's, which is depend upon the x, y, z coordinates in the Lagrangian equation, which depend upon the generalized coordinate. But here in the Hamiltonian principle, we are having the no coordinates. Everything is in the action integral from where to where the particle is moving. Hamiltonian principle is more fundamental than the other principles. What is the stationary? What is the stationary? Here we use the term stationary in the in this Hamiltonian. Then consider the two path, one from t1 to t2. Consider two path that is close to each other. Difference is infinitesimal, so the stationary means that the difference of the action integral is 0 of the first order of del qt. Then we can have the first derivative is equal to 0. Here del I, the first derivative of this integral part, action integral, is equal to 0. It means del I, which is the first derivative, which is equal to 0. Then we will define t1 to t2 lq plus del q dot plus del q dot t dt minus t1 to t2 l q dot t dt is equal to 0. We are considering the two path. One is qt generalized coordinate, second is a generalized coordinate with the constraints del qt. Now we take these two, then if we take it integral of that is equal to 0, then this will be the stationary path. So almost same as saying the minimum, it could as well as the maximum. It means del qt plus del qt2 is equal to 0 in this case. So infinitesimal part difference in here. What is del qt, which is arbitrarily sort of, and it has to be 0 at t1 to t2, and it is defined the continuous, non-singular, and continuous for the first derivative and continuous to the second derivative. That will define later. First we know that this del qt that defines the stationary value, and this will be continuous, non-singular, continuous for the first and second derivative, and this will shrink to the 0. It means alpha, we define del qt is equal to alpha nt, or we can say it is a eta t. Alpha is the parameter which will make it is the 0, and nt is arbitrary well behaved function which defines its continuous non-singular first and second derivatives of that. So nt1 is equal to nt2 is equal to 0. That is the arbitrary function. Hamiltonian to Lagrangian. How will convert the derivative Lagrangian equation from the Hamiltonian principle? The Hamiltonian principle defined by this equation, we define I alpha is equal to T1 to T2. This here we put the value of del Q. From here we put the value of del QT alpha and T, and then we have del I is then limit alpha approaches to 0. This value of alpha, here we know that alpha is the parameter whose value approaches to 0. So I alpha minus I 0, then we have del I del alpha alpha 0 del alpha d alpha. Now we must know about that del I del alpha alpha I is equal to 0, which leads to the Lagrangian equation. If we put this value here, then we can get the have the 0 value. Now from this lecture we can summarize that the derived Lagrangian equation from the Newton's equation, we are having a differential approach to define the D'Alembert principle. Or we can have some assumption that we have made. That's what are that? Constraints are holonomic that define the generalized coordinates. If the constraints are holonomic, then we can say these are the generalized coordinates. Forces of the constraints do not work, then no frictions on the system. Other forces are monogenic, where we define the generalized potential which depend upon the velocity. And we introduce the Hamiltonian principle which define the integral path. The previous defined the differential path, but here define the integral path, and we also define the action integral and the stationary part in this Hamiltonian principle. Thank you.
With this note, thank you so much for giving us this session. Friends, you can write to us at info.cec@nic.in if you have any question or if you wish to give your feedback. Friends, we are going to upload this lecture on YouTube soon. Keep watching us and keep writing us. Thank you for watching CC Gurukul Live Lectures. Thank you, and thank you once again.
Thank you.